Okay guys, the new topic is graphing exponential functions. Before we get into the graphing part, an exponential function is basically an equation. It's going to have x and y in it. It could alternatively have f of x in it. But the main thing is that the variable is in the power. So number one specifically, we've graphed something like y equals x squared. So the variable is the base, and then you remember you get this shape called a parabola. Looks kind of like that. But y equals 2 to the x power changes everything. The variable being the exponent creates a whole new shape. So I'm just going to erase that, get rid of it, and we're going to look at graphing this. Now this is a very, very basic one. Y equals 2 to the x. I'm going to go over to Desmos, which is what you're going to be wanting to use. Y equals 2. I do the power button, and then x, and then there is the graph that you can see. So it's sort of flat on the left, and then it slowly starts to curve up, and then at some point it dramatically curves and goes up. This is an example of what we would call a growth function, because the graph actually grows. It gets higher and higher. Now you can probably hear my dog's collar jingling in the background. He's trying to get up on my lap, and here he comes. So I will try to keep teaching with my little dog here. We'll see how that goes. Okay, so y equals 2 to the x. One thing to notice, it does have a y-intercept at 0, 1, so that's a good point to graph. The flat part isn't exactly flat. It actually keeps on curving, and it gets closer and closer and closer to the x-axis, but it never actually touches it. If you keep zooming in, there's always going to be a space there. And it never gets completely flat. It's always slightly curved. So the x-axis is what we refer to as an asymptote. So some people will say it gets infinitely close to that line. Infinitely close isn't really technically the right way to say it. You might say something like arbitrarily close, but the point is the graph, as it curves down, it gets really, really close without ever touching it. It's not technically parallel, because parallel would mean it becomes a straight line, and it's not straight, it's curved. The rest of the graph, I just kind of zoom up like that, like take off like a rocket. You could plot in, distinct more points, like 1, 2 is a point on the graph, so technically my curve should have gone through there as it takes off. But if you just get a reasonable ballpark graph, that's gonna be good enough. So what I have here isn't perfect, clearly, but we could call it good enough. You may see instances where when there's an asymptote, people graph a dotted line there. Maybe, maybe not. Just be familiar with the idea of an asymptote, just sort of an invisible barrier or boundary that the graph itself gets really close to but never touches. But anyway, there it is. So it's a growth function. 2 is the base, x is the power. It's called an exponential function. It has this thing called an asymptote, and that's what it looks like. The second example, y equals 3 to the x. The only reason I included this is I just want to show you that if you change the base, it doesn't change that much about the graph. It still has the same intercept, still has an asymptote here. It still takes a dramatic curve up. This time 1, 3 is on the graph instead of 1, 2. So technically speaking, having a 3 here instead of a 2 makes the curve steeper. Like if it's a rocket, it's just going a lot faster than this other graph. But if you're ballparking it, the graphs look pretty much the same. You just try to make, the bigger this number is, the steeper you make your graph. So there's the first two. The next two have fractions as bases. So we want to look at what that does. So y equals parenthesis 1 divided by 4. There's my 1/4. Go outside the parenthesis and hit the power button. And then there I put the x. And now it's virtually the same graph, but it's sort of flipped around. So the asymptote is still the x-axis, but it flattens out over to the right instead of to the left. All right, that was a little mistake. So it flattens out here, and then the curve is over there. And this is often referred to as a decay function instead of growth. So we normally look at graphs, we look at the left to right nature of it. So this starts off really, high up, and then as you move along, it gets lower and lower and lower. So a growth function, decay function instead of a growth function. Same asymptote. Same x-intercept. And then what happens if we change the base number 4 here to 1/2? Y equals parenthesis 1 divided by 2 raised to the x. This one, same y-intercept, same asymptotic behavior, same asymptote, but it's a little less steep than this one. So the type of fraction, the fact that it's a fraction makes it decay. The type of fraction can sort of affect how steep the curve is. So there's your sort of 4 basic, well, really there's only 2 basic exponential functions, the growth and the decay. I just did 2 of each type for you to look at. As we move along, we're going to now see what happens if you stick a number in front of each one. What happens if it's a positive number, a negative number, a fraction, that kind of thing. When you multiply something by a number, it's often called a coefficient. So in number 5, it's basically your y equals 2 raised to the x power graph, but there's an additional 2 multiplied in front. So here's what I'm going to do. I'm going to graph this and this at the same time, and what happened? Well, now the y-intercept is at 2. It still has the same asymptote, it still curves, and the curve isn't that much different. It's really the same curve, it's just bumped up a little bit because of the way that has happened. Number 6, let me delete these. Let's graph 2 at a time. Y equals 1/7 raised to the x, and then y equals 1/4 times 1/7 to the x. And you'll see multiplying it by a 4th sort of compressed the graph. These are both decay graphs, but now the y-intercept is at 0.25. So you just kind of estimate right around there. The asymptote is the same. It gets closer and closer to 0. It is a decay function, so it looks kind of like that. Again, just ballparking. I could go back and find very specific points if I want to try to get really, really technically correct, but we're not going to worry about that today. So multiplying by a number kind of can stretch it out so that the y-intercept gets pulled up a little from here up to here if it's multiplied by 2, or it can shrink it down so the y-intercept moves down. This one moved down to 0.25, which is the same as a quarter, 0.25. If we graph this one, now we'll just go ahead and type in y equals 1/2 raised to the x. Oops, I really messed that up. Let's fix that. Raised to the x. So there's what it would look like if that 3 wasn't there. But if we introduce that coefficient of -3, it did a couple of things. The fact that it's negative flipped it upside down, and then the y-intercept 0, 1, if all it did was flip it upside down, the y-intercept would be right about there. But it's not. The y-intercept is at -3 right there. So multiplying by the negative is what flipped it upside down. The 3 is what moved the y-intercept. We still have the same asymptote. Just looks like that. Okay. Let's Move on to number 8. So we have y equals 2 to the x. If that negative 5 wasn't there, y equals 2 raised to the x. That's our growth function, with 0, 1 being the x-intercept. Can you guess what that negative 5 is going to do? Just form a little guess in your head. Okay, if you said the negative is going to flip it upside down, you are right. And if you said 5 is going to move the y-intercept, you are right. Let's look. Y equals negative 5 times 2 raised to the x. And there it is. 0, negative 5 is the intercept. The asymptote is still the x-axis, but it curves like this. I'm not being super precise. Again, ballpark is a pretty good graph. There you go. So you are using Desmos. It does the work for you. Back in the old days, you had to make a table with y and x and plug in numbers and plot the numbers. I mean, that's a thing. You could put yourself through that if you wanted to. But we're just going to go a lot faster by using Desmos. And hopefully you still get the understanding that, hey, a fraction makes a decay function, a whole number makes a growth function. If you think about it, when you raise something to a power, you're multiplying it by itself over and over. So the higher that number x is, the more 3's you multiply together, that's going to get higher and higher answers as you go along. Alternatively, with a fraction, when you multiply something by a fraction, it gets smaller. If you multiply a fraction by itself, it gets smaller and smaller and smaller as you go. And that's why that's decay. It gets so much smaller. Say, there it is, decay. Okay, so a negative flips it upside down. Multiplying by a coefficient of a fraction sort of compresses it a little. Multiplying by a whole number sort of stretches it out a little. Essentially, you notice that in the y-intercept area. Let's go down to number 9. Now we do have an exponential function. It's multiplied by a negative coefficient, so it's going to be sort of upside down. The 4 is going to stretch it out, but then there's this minus 1 here. So here's what I'm going to do. I'm going to graph y equals negative 4, 2 to the x. Then I want you to guess at what that is going to do before I type it in. So y equals negative 4 times 2 raised to the x. Now if I do that exact same thing, times 2 raised to the x. Oops, I just remembered something I need to do. Parenthesis x. Now when I hit minus 1, there it is. The blue graph was the original graph right there. The green graph, the minus 1, basically moved it to the right 1 spot. So the minus 1 had the effect of moving this graph right 1 place. We call that a horizontal shift. So instead of making an intercept at negative 4 like on this graph, the intercept is actually negative 2. The intercept that would have been there is now to the right 1 place. We still have the same asymptote. Curves through here. Excuse my little wiggles, but I can only do so much. And if my expectations are a ballpark graph, maybe you can forgive my horrible drawing skills. But there it is. Let's look at number 10. So I know that this is going to be a decay function. I know multiplying it by 3 will stretch it out and should put an intercept at 3. But this plus 1 is going to move it horizontally. Now if a minus 1 moved it right, what do you think a plus 1 is going to do? So here's what I'll do. I will graph y equals 3 times 1/2 to the x, and then I'll do this one so you can see exactly the effect of that plus 1. Y equals 3, parenthesis 1/2 raised to the x. So that looks like this. Now I'm going to type in y equals 3 parenthesis 1 half raised to the x plus 1. That graph is in black, so the original was in purple right there, but this graph has moved left one place. So instead of having an intercept there, it's moved left one place. The new intercept is at right around here. And we draw our curve like this. Exponential decay graph like that. So we're looking for some key components. Intercepts are always good when you're graphing. The asymptote really sort of tells you exactly where to do your drawing. If you're sketching your graph and you're coming way down below the x-axis, then it's obvious you did something wrong. Or if you never quite level off to the x-axis, you're really not understanding the asymptote idea. So it kind of helps shape the graph. It's like a boundary line. Okay, number 11. Now we have a plus 2 here instead of up here with the power. So when you added or subtracted a number with the power, a minus moved it to the right, and as we saw here, a plus moved it to the left, in this case one place. If that was a 2, it would have moved it 2 places. What does a plus in this case or a minus in this case do to the graph? It's not up here anymore. So here's what I'm going to do. I'm going to graph y equals negative 1/4 2 to the x, and I'm going to graph this, and we can do a little comparison. Y equals negative 1/4 times 2 raised to the x, sort of an upside down graph. Its intercept is at negative 0.25. And then we'll graph y equals negative 1/4 2 to the x. Now I have to hit my little over arrow to type in the plus 2 here. And that plus 2 moved the graph upward. So now I have a new asymptote. This is the first time this has happened. My curve looks like this. So the original graph had the x-axis as an asymptote, and the y-intercept was negative 0.25. This plus 2 had the effect of moving the graph up 2 places. That's a vertical translation or vertical shift. And now the asymptote, well here, if I trace my finger along that line, you see 1.999. Eventually it does turn into a 2, and I told you it never actually touches the asymptote. The calculator actually makes it a 2 because at some point it has to round off. But if I zoom in here, eventually you'll see there is a space between the line and the 2. So if it ever actually turns into, in this case, a 2, it's just because it rounded off. So here's what's interesting. This number here, well, I don't like that. This number here, it's what we call a vertical shift, but it's also the horizontal asymptote. Okay, so if we look at number 12, I know that it's a growth, which looks kind of like that. It's multiplied by a half, which is going to lower the y-intercept a little bit and flatten it out. But this minus 2 means that my horizontal asymptote is going to be down at negative 2. Instead of looking like this, the whole thing moves down. So my intercept is going to be down here. It's going to come along this line and then curve upward. Let's go ahead and just graph that and see. So y equals 1/2 3 raised to the x, then hit the arrow, minus 2. And then I got to hit the home button. And there it is. Okay, my graph isn't quite curvy enough. I guess, I mean, I was close if I'm just doing it off the top of my head. But if I want a more accurate graph, still ballpark, but I'm going to curve through here and then upward, and that's what I get. Not perfect by any stretch, but I don't expect perfection, just ballpark. Of course, the answers are all here. So as you can tell, we've done things differently. I did this entire sheet for notes. The actual assignment now is going to be much shorter than this, but it's a whole separate document that you can pull up. So good luck, use Desmos, do your best to draw reasonably good ballpark graphs, don't expect perfection, and then submit it. And I hope to see some good results.